That movie really described what was about to happen on Mars for the Mars Science Laboratory, now known as Curiosity. And Curiosity did indeed land as planned and as shown in that movie. And this is a wonderful segue to our first speaker, who is Elizabeth Rampe. Liz is an exploration mission scientist at the NASA Johnson Space Center, where she researches past aqueous environments on Mars by studying the chemical weathering products on the surface. Liz is part of the science team on the Curiosity spacecraft, where she also serves as the deputy principal investigator and the instrument operations lead for the chemistry and mineralogy experiment on the spacecraft. Liz.
Great. Thanks very much. Good morning, everybody. I'm Liz Rampe. I'm a planetary geologist at JSC. And like Louise said, I'm also the deputy PI of one of the instruments on Curiosity called ChemMin. It's an X-ray diffractometer, and it tells us about the minerals that we find in the rocks and the sediments that we sample. So I'm more of a mineralogist, but it's really the sedimentology that is just completely amazing in Gale Crater. So I'll spend most of my time showing you some images of sedimentary rocks so you get an idea of what these environments were like in Gale Crater about 3.5 billion years ago. I'll also show you some evidence for groundwater and tie in a little bit of the mineralogy so you get a more complete picture of what Mars was like a few billion years ago and why we as geologists are so interested in this planet. So Curiosity landed in Gale Crater in August 2012, and Gale Crater is an impact basin. It's about 150 kilometers in diameter, and it has this mound of layered sedimentary rock in the middle called Mount Sharp. It's about 5 kilometers tall. And Curiosity landed in Gale Crater because from orbital spectral observations, we know that the lowest layers of Mount Sharp show a variation in mineralogy that may signify a dramatic climate change that happened on Mars about 3.5 billion years ago. So in those lowest layers at the base, we see a lot of phyllosilicates or clay minerals, and these require a lot of liquid water to form. In slightly higher strata, we see a lot of sulfate salts, which obviously form in more saline environments. So this change in mineralogy suggests that there was a change from a much wetter Martian environment to a much drier one. And by studying these layers with Curiosity, we can characterize these ancient environments to ultimately determine whether or not they may have been habitable to microbial life, at least by our standards of habitability on Earth. We've driven through about 400 meters of vertical stratigraphy, and this figure in the middle just shows the lower half of our stratigraphic column, shows you the types of sedimentary rocks and their thicknesses that we've studied so far. This is our traverse from our landing site to where we are today, and this was taken a little over a month ago, so we're maybe 100 meters southwest of there, up on this ridge. We've driven about 18 kilometers so far, and this shows you all of our major waypoints, but we've investigated sedimentary rocks that have been deposited by lakes, rivers, deltas, and by wind. To introduce you to some of those more important outcrops that we've investigated, very close to our landing site, those descent rockets blew away a lot of the surface dust and sediment and revealed this conglomerate, which is a very coarse-grained sedimentary rock. And the roundedness of those pebbles and the size of those pebbles suggests that this rock was deposited in a river that was up to 1 meter deep. And then further along our traverse, but still on the plains, we did a campaign at the Kimberley, and here we see these sandstone beds that are very gently dipping towards the center of the crater, and these were deposited in a delta. When we got to the base of Mount Sharp, this is where we first encountered what we call the Murray Formation. It's hundreds of meters thick, and in some places we see these intervals where there are very thinly laminated mudstone deposits or very fine-grained sedimentary rocks, and these suggest deposition in a lake environment. There are also other intervals with cross-stratification suggesting deposition by rivers and by wind. And then more recently, we were in this sort of hodgepodge of rocks that were deposited by wind, rivers, lakes, and deltas that we call the Heterolytic part of the Murray Formation. I'll show you some images from that today. Then we also have the Stimson Formation, which is a petrified dune field that overlies the Murray Formation. It just forms these gorgeous buttes. So from here, I'll take you along our traverse and show you more of these rocks and show you a depositional model for to explain our observations. So very early on in the mission, we did an extensive campaign at the Yellowknife Bay, and these are the oldest rocks that we investigated on the mission. They're made up of fractured mudstone, so very fine-grained sedimentary rock. But we see a lot of evidence for groundwater here. These raised ridges are enriched in magnesium, suggesting that there were waters enriched in magnesium moving through these sediments before they lithified. We also see these little spherules, suggesting water was percolating through pores in the sediment. We reached our target, which is the base of Mount Sharp, in September 2014 when we got to the Pahrump Hills, and this is the start of what we call the Murray Formation. For scale, this is about 12 meters of vertical stratigraphy. This yellow line is our traverse through the Pahrump Hills. These dots were stops where we took images and compositional measurements. And we actually did this 3 times and spent 5 months here characterizing these rocks. Most of the rocks we see are these laminated mudstones deposited in lakes, but we also see a lot of evidence for groundwaters here. And I know this image is small because this screen is small, but this is the Mojave 2 target, brush free of surface dust. And if you look very closely, you'll see these millimeter scale lenticular crystal pseudomorphs. They sort of look like little rice grains. They're reminiscent of gypsum, which is calcium sulfate salt. And so this suggests deposition of salts in groundwaters here. A little further down the road, we stopped at Mariahs Pass, which is where we see a contact between the Simpson Sandstone and the underlying Murray Formation. And along this contact and just above and below, we see these fractures that are bleached, suggesting that there were groundwaters moving through here leaching minerals. And just to show you some pictures of the Heterolytic Murray Formation, which is just below where we are today, we see a lot of evidence for groundwater. Here in this outcrop, you see those horizontal laminations, but you see these centimeter scale concretions. In this outcrop on the right, you see the bulk of it is red, but if you look closely along these fractures, you'll see that it's gray, suggesting that reducing rather than oxic fluids were moving through this rock after it lithified. And here in the face of this rock, you see sort of these swoopy features. This is cross stratification from the migration of ripples across the surface, either in a river or a subaerial wind environment. Again, 3.5 billion years ago on Mars. We also see evidence for desiccation. On the left is the old Socra target for a scale that's about 1 meter across. And we see these petrified or fossilized mud cracks from the subaerial desiccation of muds. On this outcrop on the right, we see these bright bedding parallel bands. Those are sulfate salts, likely from the evaporation of lake waters here. And so taking all of these images into consideration, we can come up with a depositional model to explain all of them. And so this cartoon shows you what Gale Crater was like about 3.5 billion years ago. So we would have seen streams and rivers emanating from the crater rim, likely from the melting of snow and ice. These would have deposited those conglomerates that we saw close to the landing site. And where these rivers flowed into lakes on the crater floor, that's where the deltas would have been deposited, represented by those dipping sandstones at the Kimberley. And then those laminated mudstones were deposited in these lakes, so like what we saw at Pahrump Hills and what we've seen since in the Murray Formation. Then along the lake margin, there would have been evaporation and desiccation to cause those mud cracks and the precipitation of those salts. And then we would have had groundwaters moving through here, probably not only when these rivers and lakes were present, but long afterwards to create those diagenetic features that we see. And so if we look at the mineralogy, this can give us a little more of a complete picture of what these ancient environments were like. So these pie diagrams show you the abundances of minerals in all of the rocks that were deposited in lake and river deposits along our traverse. And so I'll just point out a few of them. In black, these slices of pie are magnetite, and red is hematite. These are iron oxide minerals, but magnetite has some reduced iron, whereas hematite is only oxidized iron. And so you see a lot of these lower samples have magnetite, but these top 4 samples have a lot of hematite, suggesting oxic conditions. These yellow slices of pie are calcium sulfate salts. Again, these top 4 samples have a lot of calcium sulfate salts, and this combination of both salt and hematite suggests that these samples were deposited in more saline oxic conditions, and this change in mineralogy might represent that transition to a much drier Mars. So finally, I'm going to leave you with where we are today. We're up on this ridge called Vera Rubin Ridge, and we're here because from orbit, we identified a lot of that hematite mineral, or the iron oxide mineral. So the plan is to traverse across a portion of this ridge to measure the sedimentology, take compositional measurements to really understand how this ridge was deposited and how the hematite formed, whether it was in lake waters or groundwaters or by some other mechanism. So here's a few images as we were, before we climbed the Vera Rubin Ridge. You see these horizontal laminations with the occasional crossbed, very similar to what we saw in the Murray Formation below, suggesting a continuation in similar depositional environments. Here's an image as we are climbing the lower part of the ridge. You can see it's pretty steep, so we can handle pretty steep terrain. A nice outcrop in the middle part of the ridge showing nice laminations and surfaces where we geologists can take strikes and dips. We love that. And you probably can't see this mosaic very well, but if we stretch the colors a bit, this is from the upper part of the ridge, you can see there are all sorts of colors up here: reds, purples, blues, beiges, suggesting changes in composition here. So I'm going to leave you with this mosaic of the upper part of the ridge. Again, you see that color change, but if you look in the distance, you see some slightly higher strata. These are the strata that we're going to visit in the next couple of years. We know that from orbit they're enriched in clay minerals and sulfate salts, and so we'll continue to study these rocks to determine how these environments in Gale Crater changed over time. Thanks.
Questions on this?
Just one, maybe everybody knows this, but where do you think the water is now?
Oh, that's such a good question. So there is some water on Mars. It's not liquid water. It's in the form of ice, so we find it at the poles. We also find some in the near subsurface in mid to high latitudes. But about 3.5 billion years ago, Mars lost its magnetic field, and the magnetic field is what protects the atmosphere from erosion from high-energy particles coming in from space. So once Mars lost its magnetic field, it didn't have that protection. The atmosphere didn't have that protection, and so eventually a lot of that water was just lost to space.
Mars today is about 40 below zero. And was the orbit different back in those days? You couldn't possibly have liquid water at the orbit it's at today.
Right, so it's more about the protection of the atmosphere and this magnetic field that helped Mars maintain its water. But yes, it would have been cold, and there is this huge debate on Mars because we see all this evidence for liquid water, right? You know, the minerals, the geomorphology. So there's this massive debate about whether early Mars was warm and wet, or was it cold and icy with periodic or just little periods of warming that caused liquid water. And you know, I think a lot of people are starting to go towards that, yes, early Mars was probably much colder and icier than we think it was, and then there were maybe changes in obliquity that would have caused local warming, or maybe even volcanic eruptions that could have caused periodic warming and melting.
How do you lose a magnetic field?
Ooh, good question. So, the Earth, we have a solid inner core that's surrounded by a liquid outer core that's spinning around. This causes a dynamo, which causes a magnetic field. And so once that structure in the interior is lost, then you lose your magnetic field. And so Mars is much, about half the mass of Earth, and so it just didn't have probably enough heat to keep that going for a long period of time. don't worry about the Earth's magnetic field. We're okay. There are other things to worry about.
And just a question for me, how fast is the rover moving each day?
Oh, we move really we do not move quickly at all. It's really a snail's pace, and it really depends on where we are, about, what sort of distance we cover in a day. We can cover up to a few hundred meters or so, but a lot of times we're limited by the terrain and what we can see and how dangerous it is.
Thank you. Okay, thanks very much.
Thanks.